Good day to our great panel, Dr. Lo Chang Yi and Dr. Ram Husaini. Today I'm going to present the progress of PSM 1 entitled Determine of Oil Palm Fruit Ripeness using Dilated Measurement Technique. My name is Shamala Kalaiselvan. My metric number is CD 190069. My supervisor name is Dr. Ong Pauline. In the global market, palm oil has experienced rapid and sustained growth. Oil palm was first introduced to Malaysia as an ornamental plant in 1817. The production of crude palm oil was 18.1 million tons based on the information gathered from Malaysia Palm Oil Board. Oil palm fresh fruit bunch is the main product that is harvested from oil palm plantation to produce palm oil. The fruit should be picked at the correct time because if they become too ripe, many clusters will fall and quality of the fruit will degrade. Oil palm ripeness can be categorized into three parts, which is ripe, unripe, and overripe. A ripe bunch is a fresh bunch with a reddish orange color and an orange mesocrop on the outer layer of the fruitlet. An unripe bunch is a fresh bunch with a reddish orange or purple red color and the yellowish orange mesocrop on the outer of the fruitlet, and the overripe bunch as a carmine color. The traditional method to determine the ripeness of oil palm, which is heavily reliant on the color of the fruit. However, there are still many issues being faced by the oil palm industry. One of the most important issues is the quality of the harvested palm fruit. The manual technique that is utilized, visual inspection in fresh fruit bunch grading, is less accurate. The probability of harvesting unripe FFB eventually will be a reason for financial losses when the quality of manufactured product was being affected by low quality fresh fruit bunch. This method also a time consuming and also could lead to production costs. The first objective of this study is to study the dielectric properties of oil palm fruits at different ripeness stages. And the second objective is to apply different machine learning model in the classification of oil palm fruit ripeness based on the dielectric properties. The first scope of this study is oil palm fruits are classified into categories of unripe, ripe, and overripe. The second scope of this study is dielectric properties of oil palm fruit are measured in the frequency range of first 1 GHz to 8 GHz. The third scope of this study is simulation of this project were carried out using MATLAB software. And the last scope of this study is 1D convolutional neural network, support vector machine, and k nearest neighbor are used to classify the ripeness of oil palm fruit. This significance of this study is the grading method based on the dielectric properties will be able to classify the ripeness of FFB in a non-destructive manner. As one of the leading oil palm producer, the country required an automatic system to assist farmers and small farmers in grading the oil palm fruits. The possibility of an automatic grading system for replacing manual grading by workers is shown in this study. The outcome of this study has a potential to be used as an automatic grading system in the production of palm oil. This would eventually help to reduce the time and cost required to produce high quality of palm oil. Sustainably, there is a considerable demand in the market and industrial sector for higher quality of palm oil fresh fruit bunch. Oil palm fruits growers commonly utilize their experience to estimate the best time to harvest based on the color variation of the fruit. However, this method is unreliable and cannot guarantee the quality of oil palm fruit due to the fast changes in the ripening and growing of the fruit. Furthermore, several factors influence fruit maturity, including climate variation, air temperature, soil moisture, soil fertilizer, air relation, and humidity. As a result, developing a quick and non-destructive way to determine the internal quality of oil palm fruit using an impedance measurement technique and coupled with CNN, CNN, SVM, and KNN, which could provide a suitable estimation method. Fruit waste can be reduced because the fruit does not need to chop to be measured. There is no need to use a specific equipment or chemical analysis to determine the ripeness of oil palm fruit when applying the non-destructive method. Each palm tree generates a few bunches of FFB. Depending on the age of the tree, a mature palm carries 1,000 to 4,000 fruits. Each fruitlet has about 5 to 8% kernel. Mesocrop is also referred as palm oil, crude palm oil, and mesocrop oil. The percentage of mesocrop is in each fruitlet ranged from 85 and 92%. Aloes oleifera and Aloes chinensis are two principal species of palm oil. Palm oil beneficial characteristics such as reasonable height increment, high unsaturation, and resistance to fusarium wilt. It also contains functional genetic variation that can be incorporated into breeding programs for the creation of improved commercial variant of E. genesis. Aloes chinensis come in three variants, that is Piscifera, Dora, and Terra. Piscifera was a pollen type, while Dora has a thick shell and less oil. Tenera is a combination between Piscifera and Dora. Tenera palm fruit is usually planted in Malaysia because of its commercial and processing viability, since harvesting is more accessible. The palm trees are generally shorter, produce a good fruit bunch, and a higher fruit oil content. There are few methods to determine the oil palm fruit ripeness that have been done by the previous work. The first technique is Florence's technique. The grading system using Florence's technique to differentiate oil palm fresh fruit bunch into three categories have been studied by Hazil. The Florence sensor has great potential and can be used in a fresh fruit bunch grading system for oil palm. In combination with the statistical analysis, the blue to red fluorescence ratio parameter proved to be an accurate indicator with statistically significant differences across the three categories of oil palm fresh fruit bunch maturity. The second technique is inductive sensor technique, has been applied by Shamala, a simple and non-invasive inductive sensor system for identifying the ripeness and forecasting harvest time of oil fresh fruit bunch. In combination with the discriminant analysis and polynomial regression, the inductive sensor system could accurately assess the maturity of oil palm with the precision of 100%. The third technique is image processing technique that is applied by Septiarini. Since the maturity of fresh fruit bunch may be determined based on the color, hence image processing can be applied. Image processing for the classification of oil palm fruit into underripe, ripe, and overripe. The study utilized the OTSU technique for oil palm fruit segmentation. Color extraction features were used by calculating two types of features, that is including the mean and standard deviation based on four color component, that is red, green, blue, and gray, resulting in the production of 8 features. Convolutional neural network technique is applied by Ibrahim. Convolutional neural network technique has become a most advanced computer vision technique, especially for feature extraction where it is very accurate. This study compares CNN, the pre-trained CNN model, and a handcraft feature, and classify techniques for reorganizing the ripeness in oil palm fresh fruit bunch. Color movement, fast retina key point, binary features and histogram of oriented gradient texture feature is with support vector machine classify the among the band corrected features. The next technique is near infrared spectroscopy technique that is applied by Silahi. Near infrared spectroscopy technique, a rapid and non-destructive technique to access the ripeness of fresh fruit bunch. NIR was combined with the principal component analysis and linear discriminant analysis to provide an alternative approach for classifying the maturity of oil palm fresh fruit bunch. The last technique is applied by Raj, the Raman spectroscopy technique. The Raman spectroscopy technique is a quick and non-invasive and reliable method to determine the ripeness of oil palm fruit bunch. In addition, this method is resistant to the impact of light and moisture-induced noise. The dielectric properties has gained a greater attention in ripeness of oil palm fruit bunch. The measuring techniques applicable to any desired application are determined by the nature of dielectric substances to be tested, both physically and electrically. The dielectric characteristics are consequences of electromagnetic radiation interacting with its component at the cellular and molecular levels. The features of dielectric properties is a relative permittivity may reach values up to 10 to the power of 6 or 10 to the power of 7. At frequencies below 100 Hz, it drops at high frequencies in 3 major increments known as dispersions. In an electric field, essentially no current flow through the dielectrics because there is no weakly bonds or free electrons that may flow through the material. Therefore, the methodology of this research starts off from oil palm sample preparation. In this study, 30 samples of oil palm fresh fruit bunch will be collected from the oil palm plantation in Kalaiselvan, where 10 of oil palm fruit are unripe, 10 of ripe category, and another 10 for the unripe category. From each samples, 20 fruitless were randomly picked. After that, the measurement of impedance will start using a pair of electrocardiogram ECG electrodes connected to an impedance analyzer board AD5933 and the computer. The impedance measurement of each fruitless is measured. The ECG electrodes consisted of a small metal plate surrounded by the adhesive pad that was coated with the conductive gel to aid in electrical signal transmission. The impedance measurement was measured in a frequency range from 1 to 8 GHz. After that, the spectral pre-processing. Prior to the multivariate data analysis, the raw spectral were pre-processed to improve the quality of the absorption characteristic and minimize the spectral variability. In this work, the pre-treatment techniques standard normal variation, variate SNV, multiplicative scatter correction MSV, detrend, and first derivative as well as their combination were utilized. After that, the sample deviation. The sample were divided into calibration and prediction groups at the ratio of 2:1. The calibration set samples were used to create a model, while the prediction set samples were used to validate the model. For data partitioning, the sample sets partitioning method based on joint X and Y distance and extended from the signal Kenneth-Stone techniques were used. SPXY, unlike KS algorithm, evaluated both spectra and references well. Next is variable selection. The principal component analysis PCA techniques, as well known as a commonly used data reduction method, was used in the study to improve the efficiency and speed of the data analysis. The original wavelength variable were transformed to function of the original wavelength variable using PCA. The PCA removed spectral data variables. that were similar and had a high correlation with one another. The principal component have reduced variable numbers, but they still count for majority of variable measure spectral variables. For the performance evaluation, the calibration and validation accuracy were measured using a correlation coefficient, root mean square error of calibration, root mean square error of predictions, and ratio performance deviations. The last method is modeling method. In this study, three nonlinear modeling method, that is CNN, SVM, and KNN, and the two linear modeling method, that is multiple linear regression and PLSR, were employed to extinguish determine the ripeness of oil palm. These are the experiments set up for the impedance measurement. The laptop is connected to the impedance analysis board, and the oil pump fruit is connected to the electrodiagram ECG probe. The expected result of this study is the dielectric properties of the palm oil fruit can be correlated with the ripeness of fruit, where the machine learning model can be able to determine the different level of ripeness. That's all from me. Thank you.